The other stream is the water, which you're taking the iron out of. After the iron's removed, you then neutralize the pH. That goes back to the stream, that goes into the stream, and where it will no longer harm fish. Say it one more time. How much of the iron has to be removed for the water to be safe? So yeah, I want to be clear about this again. Iron is really not toxic to people, but it is harmful to fish. And I don't know, the standard we use is 1 milligram per liter. The mine that I'm working on here, the source water is 340 milligrams per liter. So there's a lot to take out. Yeah.
Would the plant be processing the entire flow of one of these locations, or a part of it?
That's the overall objective. That's what I'd like to do. I'd like to build these plants to treat all of the water. But we're not there yet. Right now I'm seeking money for a smaller plant, really a demonstration plant, something that'll work 24/7 and treat just a portion of the water.
So you said you're doing this to cut down on the pollution, just pretty much for the fish like in the water, because you said it's not actually toxic. But what kind of byproducts are actually coming off of doing this? Is it anything harmful or anything like that?
Byproducts from the process? No, not really. So we go through a fair amount of chemical to neutralize the water. We need a lot of base, and to buy that is fairly expensive. But no, so I'm sorry. The question was what harmful byproducts are from this process, and there really aren't any. Yeah.
This might be hard to answer just because you're still working on funding to actually build a pilot plant. But do you have any idea what your work to output ratio is now that you have your process? How much work it takes to get X amount of pigment?
So the question is, what's the work to output ratio? How much work do we have to do to get a certain amount of pigment? And so I'm going to answer your question, but this is going to take a second. In getting funding for this, as I said, I started this about 10 years ago. It's been difficult to get funding for this through the normal channels because this is not really basic research. It's kind of applied. So I've pieced together research a variety of ways. One of them is I teach environmental senior design class. So I've had the students in this class design this process in various years. And this is one group out collecting samples on a very cold day. And this is the plant that one of my design teams designed. And they estimated to treat that TrueTown seep, which I've talked about, which pumps out 1 million gallons per day, it would cost $3.4 million to build, and then to operate it would cost $725,000 a year. So most of that goes towards neutralizing the acid, which will protect fish. It also covers operating costs and personnel to run the plant. But we could sell over $1 million a year in pigment. So we should be able to treat the water, run the plant, sell pigment, and make money all at the same time.
Can I ask a question? You said that the majority of the expenditures are on utilization of acid. Do you think there is a way, as a future research, to find a natural way or some natural waste that can be used for acid utilization to save more money and also save resources?
Yeah, that's a great question. So the question was, since it's so expensive to neutralize the acid, maybe there's a more natural way or a cheaper way to do that. And yeah, we are looking at that actually. And I don't know, so this plant, this demonstration plant, we're looking at using a slag bed. Slag is a waste product from the steel manufacturing industry, so it's very cheap. It's their hazardous waste, and it's hazardous because it's really high in pH. It's really basic. So we can take their basic high pH waste, mix it with our acid low pH waste, and neutralize both of them. So, but there's problems with it too.
So did you say that the water treatment facility would only deal with one drainage site, or would it work with multiple sites underground?
Yeah, so the question is, would this only work at one site or multiple sites? And yeah, we would have to build a little water treatment plant at each site, simply because it's too expensive to truck the water around, and they're too far apart from one another in most cases. If this did ever get it, or when this gets off the ground, I should say, we could have a centralized plant for like the pigment processing, for the sludge processing. So there would be separate little plants at each of the acid mine drainage seeps that treat the water, and then the sludge that gets collected all gets brought to one spot for processing.
How different are various mine runoff? Is there a wide variety of how you might have to process it, or the different things you have to take into account for mines in other states, or what the rest of it is?
Yeah, that's a great question. So the question was, how different are the acid mine drainage seeps from site to site? And that is a big, I wouldn't say problem, but that does limit this process. The mines that I'm targeting around here, their chemistry is very high in iron and is very low in other metals. So this really only works in geologic regions where that's the case. That's fairly common around here, but there are some mines around here that are high enough in aluminum, they have a fairly high aluminum content, that this process would not work there, at least as I've got it right now. There's other mines out west that are in a similar situation where the runoff is a mixture of metals and not pure iron. I have done a little work looking at separating the metals, and I think that's possible, but I want to do the easy stuff first. Yeah.
You may have already said this, but what is the range of pH you're seeing at these drainage sites, and what's the range, or what's the pH of the current?
Yeah, so what's the range of pH at these sites? It's horrendous what we find out in the streams. And actually, I should say, it's gotten a lot better. The watershed groups in Ohio Department of Natural Resources has done a lot of work cleaning up the streams in the region. The ones that I'm talking about are the ones that are really high flow rate and really acidic, and there's just no good technology for them right now. But those sites, once the mine drainage gets completely oxidized, the water itself can be negative pH. You won't find that in the stream. And when you measure it coming out of the mine, you'll see pHs between 2, 4, 5, something like that. But that's because the chemistry hasn't fully reached equilibrium yet. But you know, anything below 7 can be dangerous to high quality fish. So yeah, it's bad.
You have to deal with, in your settling tank, are there sulfate minerals that drop out at all when you raise the pH of it? Or is that like because of the composition, you don't really have to worry about it?
No, we don't get much sulfate accumulation. We actually tested that, and we're expecting that, but we don't. For whatever reason, the sulfate solids do not form. We did find that if we triple or quadruple the sulfate concentrations, we do start to see sulfate in or sulfur in our pigment, but no, it's not an issue. I don't know why. All right, so that is the science and engineering side of this. As I said, research-wise, there's a few other things I'm working on to optimize the process to make things faster and better. But I'm really at the stage now where I want to start building something and cleaning up streams. So I'm at a crossroads, and I think there's a lot of good work here, but it wasn't really until I got an artist involved that things started to change. That's when this project really started to get traction, and I would like to introduce my colleague John Sabra, who's been a big help on this.
Hi. Ooh, good job, you turned that right on, that was quick. I'm John Sabra, I'm a professor of art in the School of Art plus Design here, and I chair the painting and drawing program here as well. I'm going to talk a little bit about what Guy asked me to do to come in for the project and how that evolved from there. Talk a little bit about where my art derives from and how that relates to these pigments and things. And then I brought a bunch of supplies, and anybody that wants to make a painting, we can make a painting in like 2 seconds and you'll look like a genius. So it'll be great. Genius might be a little genius. Okay, so, so Guy comes to me and he's like, I have this stuff, or actually, so Athens is, a lot of you are maybe Athenians yourselves, so you know how things happen here. So, like, this person whose kid played soccer with my kid, we're at the rec league together, and the kids are out there, playing in the mud. And she just turns to me and says, well, I got a friend of mine, and he's working on this thing, and needs somebody who can do, like, artist pigment stuff. And I was like, yeah, sure, that's good. So that's when we had coffee. I think it was at Wits, I can't remember, but maybe it was uptown back in 1937. And he's like, well, we've got these pigments, just like you described to you. They're kind of brown, we need pigments, they need to be like high quality, otherwise the whole idea of this selling and being profitable is just not going to work. And I was like, and I don't know. So as an artist, my head kind of, I hear one thing and then my mind turns into like a million things before I turn around and do something else. So I was like, no, here's what has to happen, Art has to be huge and sexy and awesome, and then people will see it and they'll like what we do, like, got excited about it. Fantastic. So it was really fun to see those different colors that came out of it, and I've been an environmental activist my entire career, so it was a natural sort of mix for me to get involved in that. And once we started processing it, we got through this, we got through the pigments, we got them finer, we got them more specific, we got the colors so they're luxurious, because I paint in oils and acrylics all the time. So for me, the touch of a pigment, how it sits on a canvas, how it sits on a brush, how it cleans up, how it blends with other colors,